Thank you, everyone. It's a pleasure to be here tonight. Thank you for the humbling introduction there, Daniel. What I'm going to talk about tonight is a story that's quite close to my heart and actually quite close to my home. I live in the Hokianga in the far north of New Zealand, and the site I'm going to be talking about tonight is perhaps 10 kilometres from our house. My partner Diane and I have been visiting this locality. Started in about 2009. It's on private property, and we were interested in following the stream during one summer. And as we worked our way up the stream, looking at the geology and the rocks, I started noticing fossil bryozoans, which piqued my interest because I'd just been working on bryozoans, as you mentioned, for my PhD at Auckland University. So I'll get into that in a minute. Just a very brief background on myself. My name, Seabourne, I wasn't given this name because I study bryozoans. It's actually a name I was given at birth because my parents were lighthouse keepers when I was born. So it goes back to the end of the Marlborough Sounds where I come from. I grew up, though, mainly down near Dunedin and started collecting fossils eagerly as a child. We used to go on school holidays up to a place called Teshmakers, which is just south of Oamaru in North Otago. And wandering the hills during those school holidays, I came across the Ototra limestone, which is chocker full of bryozoans. So I didn't realize it then, but it's interesting that started at an early age. And in fact, many years later, I've gone back to re-look at some of the bryozoans in that same area near Teshmakers, Fortification Road, as Daphne knows all about. So studying fossil fish was my passion during my early university years. Did my master's, as Daniel has said, with you in Fordyce. I was given a really good introduction to vertebrate paleontology. But when time came to do my PhD, I headed north, got to Auckland, and Jack Grant Mackey and Kathy Campbell steered me into a fairly new topic for me, bryozoans at that time. Fabulous time I had doing my PhD down in the Wanganui Basin, looking at these amazing layer cake stratigraphy full of mollusk fossils and bryozoans from the Pleistocene. So yeah, I was primed on bryozoans when I moved north and headed up to the Hokianga during my PhD and settled up here. So then to find bryozoans only 10 kilometres away, Miocene ones in a stream bed, it got me started. So I've been working on this in my spare time, this site. So the story begins. If we go back to the earliest Miocene, Waitakian stage, very significant time in the history of Northland and northern New Zealand. What we had happening at that time was the arrival and accretion of this huge slab or terrain, if you like, of sediments and volcanics brought in from the northeast. And during this period where the compressive regime was happening in Northland, it was accreted to the area. The proto-Northland, if you like, was basically covered by what we call the allochthon, a complex sequence of sedimentary, Paleogene sedimentary rocks, Cretaceous sedimentary rocks, Cretaceous volcanics, all with oceanic origins, but brought in and placed in Northland. So this is something that Bruce Hayward, Bernard Spawley, Larry will know about this. It's something that has puzzled geologists for a long time, and slowly and surely the stratigraphy and the understanding of the allochthon is getting clearer and clearer, which is fabulous. But that's another topic. We're really dealing with what happened when the allochthon had arrived and was being emplaced in Northland. We had compression from the northeast, this material brought in and uplifted above the subduction zone, if you like, to form these enormous nap-like folds, and there was upthrust movement, and we had these depressions forming simultaneously on the top of the allochthon where sediments could accumulate, and these we call piggyback basins, as it was on top of the allochthon or the terrain. This is one of Bruce's cross sections through Northland, and this shows the rocks as they are today. But what the main things to take out of this is we have a basement comprising several terrains, Murahiku to the west and Waipapa terrain to the east, and the basement has been uplifted from the east side. You'll see at the top of the basement tilts down towards the west. And in the green here, we've got a very simplified slab of rocks that are displaced. They've been brought in onto the top of the basement and pushed across and uplifted to form Northland. So the green is the allochthon in Bruce's cross-section here. And the orange are sedimentary rocks, and up here we just have a little schematic of a basin on the top of the allochthon. We also have some volcanics here, more recent, and we have in place sediments in other parts of Northland that date to the Oligocene, but within the allochthon itself, these are foreign rocks, if you like, brought into the area. But our focus is really the early Miocene. Once this mass had started moving in, interesting things started to happen. The Hokianga area was the site of a roughly 60 by 30 kilometer piggyback basin on top of the allochthon. And it was in this basin that the main cover of the allochthon, the Cretaceous to Paleogene sediment, started eroding as it was being uplifted and started to fill in that piggyback basin. So this formed a thick sequence of marine sediment at the time, roughly 2 kilometers of early Miocene age, what we call the Altawa group, were deposited in the Hokianga basin. There's a little map here which shows roughly the area we're talking about, the west coast of Northland, Hokianga Harbour stretching inland. Just below, we have another map showing there's the Hokianga Harbour, Opanoni. Most people will know where that is. It's about 15 kilometres away from the Waimaku Valley, which is where we are located, and also where the Taita fossil locality is located. So today, the Otawa group sediments are exposed next to a fairly large uplifted block of allochthonous volcanics, Cretaceous age, what we call Tangahua group or Tangahua complex, oceanic basalts, quite worn pillow lavas, quite erosion resistant. So they form an uplifted block just north of where our fossil locality is, and the drainage patterns show that this is quite a erosion resistant high ground. In fact, the highest point in Northland, Te Rapua, is 781 meters, not far from our Taita Stream locality. The piggyback basin, so it gradually filled during the Miocene, during the Otaian, a lot of sediment building up in there. The compression of the allochthon caused further uplift of the piggyback basin, becoming raised close to shallow depths to sea level. So it's actually a regressive sequence that we see in the basin. Here is another map from Bruce, which shows the Hokianga area again. Here is in purple that block of uplifted volcanics, Whirinaki-Waimar range. And below that is part of the Hokianga basin. The green and the orange are sediments infilling the orange is the sediment infilling the basin. The green is actually more of the allochthon. But running through the center of what is now the Waimamaku Valley, we have a large anticline, the axis pretty much running northwest, southeast, and the cross sections here show the Waimar range in purple again, and the anticline, which has now there's the remnants of that piggyback basin, but it's now inverted, if you like. The strata, which was once a depression, has now been uplifted and eroded. So it's like you've got the reverse. You now have a large fold. And to find what was infilling that basin, we have to go out to the edges. So the orange, again, is the Otawa group. And within that sequence of Otawa group, marine mudstones and sandstones, is a formation that we're particularly interested in called the Waitiiti Formation. And the Waitiiti Formation is the unit where the fossils I'm going to be talking about come from. Just as a note, the Taita Stream catchment, so the anticline being eroded has formed a valley. The softer sediment in the middle has been gouged out by the Weka Weka Waimamaku River, which flows through pretty much along the axis of the anticline, but then makes a turn and comes out to the coast. But the Taita Stream bisects that, so it's running at a right angle up towards the Waimar range. It actually drains from this high ground at almost 90 degrees to the anticline axis. So as we walked up the Taita Stream that day, we were progressively walking from the center of the anticline, the older rocks, towards these younger rocks as we headed upstream. So we are able to map our way up these rocks towards eventually an overthrust of volcanics, which we didn't see because it's covered by subsidence. Here we are at Taita Stream. It's a beautiful, clear Northland stream, quite rare in Northland to have such lovely clear water running down from a largely forested catchment up in the Waimar range. So we walked up the stream and found ourselves in the Waitiiti Formation. As I say, it's a broadly regressive, so it's getting shallower. At the very uppermost part of the unit, before we get into that fault-bounded volcanics, we find probably the most interesting and fossil-rich part of the Waitiiti Formation. There are coarser deposits with macrofossils in these stream beds. Banks on the side of the stream will contain grit layers, shells washing out of the mudstone matrix. It becomes definitely more macrofossil rich as we go up the Taita Stream. Elsewhere in the valley, the Waitiiti Formation has been studied before and is well known for its micromollusks. Tiny gastropods in particular were studied by Charlie Laws. There are large forams out towards an exposure of the Waitiiti Formation further towards the Hokianga harbour mouth. So yeah, the unit has revealed a number of smaller interesting fossils, but really up until now, up towards the top of the Taita was overlooked. So seeing the Bryozoans washing out here got us very excited. It's just a little schematic of some of the outcrops exposed in the stream bed and the banks along the side of the stream. We first started going there before Cyclone Wilma, and the change of that, we lost quite a few of these stream bank deposits, and every time we've been back, it's changed. There've been new exposures and other exposures lost forever. I must say I haven't been back there for probably 4 years now. Been meaning to, but just been too busy working on other things. Fossil recovery. So initially involved walking up the stream, just picking up what we could find in the water and sticking out of the bank. But we started getting a bit more systematic after we realized just how spectacular and how important these fossils could be. At one particular bank in the stream, we have these huge boulders coming out, and you might notice they're quite spherical. And these are what we call concretions, but there's something a little bit special about these, which I'll get into. So there are channel deposits where you've got coarser material, like some of these boulders. There are some gritty, pebbly horizons. These are pictures of Diane, my partner, exploring the waters, which can be quite nice on a summer's day, but on a winter's afternoon, it's freezing in there. But great fun, great place to explore. As I say, it's all on private property, so permission was duly sought after and granted after a lot of liaising with the landowner. So not just anyone can go here, unfortunately. What did we find? Well, one of the most amazing things that turned up were these huge, spectacular pieces of reef coral. This one on the right here, which is probably Leptastria, this is a large piece, probably weighs 2 kilograms. This was lying in the stream bed, and it's a member of the family Favidae. So they're hermatypic corals that are found in subtropical to tropical waters today. So you need really to have quite warm temperatures. And to get a piece this size, this thing had been living for quite a long time. Over to the upper left is Cyphastria, and a different favid coral that had been bored into. There were holes in the pieces of coral, quite spherical holes going right through it. And we even found in some of those holes little casts of these burrows, if you like, or these little borings. So yeah, they've been exposed to bioerosion. There's another encrusting coralline beside me. I might just, if you look, I don't know if you've got my picture on screen, but I've got one of these pieces of coral here. It's about a couple of kgs, this one, decent sized chunk. So we probably have about 5 or 6, half a dozen pieces of these very large reef corals. Down the bottom of the Taita Stream, we have a local farmer, Ernie Wilkins, and chatting to him one day, he said, "Gee, Seabourne, have a look what I found in the paddock." And he proceeded to show me a couple of pieces of reef coral that he had dug up. Now his property is right at the sort of outflow, if you like, of the Taita Stream into the Waimamaku River, and we can only speculate that these pieces of coral have washed their way downstream many hundreds of years ago, perhaps, to end up in his on his piece of land. His bits of coral were very, very eroded, water-worn. All the scepter of each corallite has been eroded away. You just have this amazing honeycomb sort of looking rock. And when I told him that it was a reef coral, he was yeah, quite amazed. He's kindly donated those pieces to us. So the reef corals are a spectacular part of the fauna from the Waitiiti Formation. Just a few representative mollusks here. They're not especially abundant up the Taita Stream, but when you do find them, there's some very nice gastropods. Bathytoma, this beautiful sculpted gastropod in the center. This one next to it is Animalda robusta, the big Barryspira, the big Animalda. These are all typical Otaian warm water mollusks. There are occasional turritellids. Bivalves are not so common up the Taita Stream. They tend to erode out. You get the odd cast of a bivalve, like a cuculea or some other double valve beast. We do get the odd pectinid. Ceropectin does occur. Ostrea, little, very small oysters. But those borings I showed you in the coral, one of those boring mollusks may be represented down on the lower right there. That's a pholad bivalve. It's quite small. That's only 1 centimeter long. And that could have been one of the coral borers or rock boring bivalves that caused those circular holes in the coral. This is another boring bivalve in a piece of rock in one of those lithic clasts in the Waitiiti Formation, still preserved in its burrow. This is probably a different species to the pholad on the right. So yeah, there are some nice mollusks, but not as many as we would like. However, rhodoliths, wow, the rhodoliths are spectacular up the Waitiiti, upper section of the Waitiiti Formation in the Taita Stream. These are non-geniculate coralline algae that have grown mainly around lithic clasts. You can just see coralline incrustation on this piece of rock. Some more rhodoliths in various shapes and sizes below. So yeah, they are quite a striking feature of the upper Waitiiti and the Taita Stream. Probably a couple of different species, pretty hard to identify them beyond Lithothamnion spur. I haven't been able to get a clear idea of some of these, but we do know that they were the sort of organisms that like shallow, very shallow water. They like lots of light to grow well. The growth rates of rhodolith coralline algae is less than 1 millimeter per year. So some of these thick incrustations, they've been growing for, over a decade, which tells you that on the shallow sea floor, we had quite a stable, photically anyway, a stable environment with lots of light, warm water. Well, the temperature's not so significant for rhodoliths, but certainly an environment where the sedimentation was low enough, or there was enough water movement to keep sediment bypassing for the rhodoliths to form. And you'll notice that a lot of the lithic encrusted lithic fragments, the rhodolith goes right around the entire surface. So both sides of the rock will be covered by coralline algae. These ones, if you flip them over, they would look the same. So that tells you that these have actually moved. So the different surfaces, the undersurface of the pebble or the cobble has been exposed to the light, so it's been tipped over. So there was some movement of these clasts, or rhodoliths were continuing to move over time, allowing the full incrustation of the core of them. Some of the rhodoliths themselves have been encrusted by other animals, including bryozoans. So here we go into everyone's favorite, the bryozoan fauna. Spectacular colonies of bryozoans, for those of you who are maybe not so familiar with bryozoans. So these are, they're wholly aquatic, the majority of them, so they form colonies comprised of individuals that may have particular role or structural characteristics that all contribute to a colony. Individuals are called zooids, and they have a calcium carbonate skeleton, if you like, which is like a little box or a tube, depending on which order you're dealing with. In New Zealand today, New Zealand has one of the most diverse bryozoan faunas today on the shelf, and right down to the deepest parts of the trench. We have a bit over 1,000 modern species. Individuals are generally, the individual zooids are generally under 1 millimeter, sometimes a little bit bigger, but generally under 1 millimeter in size. So they require a microscope to really identify them. Colonies, though, may reach up, 10, 12 plus centimeters across, and they come in different shapes and sizes as well, different growth modes. So there's a lot of interesting things to look for in bryozoan remains. So back up the Taita Stream, if you pick up a rock coming out of the Waitiiti Formation, chances are that it'll have a bryozoan growing on it. So bryozoans live on hard substrates, rocks, shells. Today it can be pieces of plastic or boat hulls or bottles, but back in the Miocene, the pieces of Northland or Lachlan that were on the seafloor, hard rocks, other dead shells, rhodoliths, which have a hard surface, they all formed a place where bryozoans could settle and grow. We have a cobble shown here on the left, which has one single colony of bryozoa growing across the surface and below. Another colony shown here. You may just be able to make out tiny little individual, like little box-like depressions here that you can just see. Each one of those would have housed an individual. Each one of those was an individual within that colony. It's quite a big colony on that rock there. This little insert on the right shows a different type of bryozoan. It's from another encrusting an order that produced these radiating circular cup-like colonies. Looks a little bit like coral, but they're in fact bryozoans, and that's encrusting a rock or a rhodolith. So we often find more than one bryozoan occupying a hard substrate. So they're actually competing or interacting as they try and use up the space available on a rock or on a shell. It's a very, very interesting thing. Just briefly, most of the bryozoans that we find encrusting pieces of rock from the Waitiiti Formation are all relatives of shallow shelf species today. So we can find living representatives of most of the genera in the Waitiiti Formation still living today around New Zealand, and most of the ones up the Taita Stream tell us that it was once a very shallow marine environment with low obviously low sedimentation. Again, these are filter feeding animals. Each of those individuals has a tiny little ring of tentacles that come out and catches planktonic organisms to feed on, diatoms, very small bits of algae. They don't like high sedimentation. So again, it's telling you that there wasn't a lot of mud raining down on these things. Some more photos of pieces of rock encrusted by bryozoan colonies. These, you can see why they were called lace corals or moss animals, just covering the surface. In this case, it was a rhodolith being encrusted by a bryozoan. Up on the upper types of bryozoans, there's one colony here. Sorry, the internet's dropping out of it there. So we've got one colony in the upper left corner, another different species meeting that one. So this is what we call a colony interaction, an interspecific interaction between these two. Up on the upper right, you'll see a few different bryozoans again, encrusting just a small part of a pebble from the Waitiiti Formation. Another group of bryozoans overgrowing each other on these rock surfaces. Washing out of the banks are pieces of erect bryozoans. So not all bryozoans stayed flat and covered a surface. Some of them reached up into the water column to better access food. They might have formed a colony several centimeters high that looked like a miniature tree. We have living representatives of most of the species today, or of the same genera anyway. This one in the middle. These fragments have all washed out of the bank into the stream. So if you dig up a piece of the stream sediment, put it through a sieve, you can find hundreds and hundreds of pieces of erect bryozoan colonies that have broken up into their little segments. Some were a little bit more lobe-shaped, flatter. Some were quite cylindrical. They all have things to tell you about the marine environment, and taphonomy of these things, how they break up, how worn they are. The insert on the lower right is a beautiful SEM, the scanning electron microscope of one of the bryozoans from the Waitiiti Formation, and you might be able to make out some of the intricate structure of the individual animals within that colony branch. Again, they typify environments where the sedimentation is either low or the sediment is moving through and allowing the bryozoans to filter feed effectively. We found a lot. I was lucky enough to get Dennis Gordon, New Zealand expert bryozoologist, to come up to the Hokianga and visit the site with us and examine some of the material we'd collected. So we have over 400 colonies collected and a minimum diversity of 74 taxa. And of those, 59 were chylostomes. So there are two main orders of bryozoans found living today in marine environments. Chylostomata, or chylostomes, are the most abundant in terms of diversity in the Waitiiti Formation, but we do find, we had 15 cyclostome representatives. This sort of ratio is pretty common for most environments today, where the chylostomes are dominant. What do they grow on? Well, we found that the rocks produced an enormous amount of, they hosted a lot of encrusting bryozoans and the rhodoliths. But we also found them encrusting shells and forams. And the different shapes of the colonies, most of them were encrusting, but we did find a couple of different types of erect or tree-like colonies, and a couple of bryozoans that form lumps. They encrust themselves, if you like, to form a sort of a multi-layered, massive type colony. So lots of different types, different shapes of bryozoans. The foraminifera I was talking about, wow. Most obvious and most spectacular are the lepidocyclinas from the Waitiiti Formation. They get big. We couldn't believe it when after Cyclone Wilma, a bank had collapsed and we saw a couple of these things that were over 5 centimeters across. So huge in the world of forams, and actually up to a couple of millimeters plus, especially in the central part of the test. They were extremely impressive. This one is probably the largest foram known from New Zealand. There are other large forams besides Lepidocyclina. We have some Criborotalia, but they're not as common. We collected 256 large Lepidocyclinas, but of those, only 30 were over 3 centimeters across. So yeah, the bigger they are, the rarer they are. Obviously, the longer these things lived as well. They were older when they in lifespan. And interesting to note, I found a study done in Iran, published in 2009, where they also had a deposit where Lepidocyclina were extremely common, of similar size, 6 centimeters across. They examined their large forams and found that of those larger Lepidocyclina, some of them had been encrusted by bryozoans. Now, they noted that Lepidocyclina seems to be the only foram that hosts bryozoans in their study. They looked at 1,600 tests and found that only 10% of the bigger ones had bryozoans growing on them, but they managed to find 34 species of bryozoans on their Lepidocyclina. Well, guess what? We have them too. Some of the bigger forams hosted bryozoan colonies, or were encrusted in some cases by multiple bryozoan colonies. Pretty neat. So far, we're up to just over 25 different species of bryozoans growing on top of the foram tests. That the most abundant taxa were Figularia and Disparella, cyclostome, Macropora, Crassimarginatella. These are all bryozoan taxa, but the Figularia is an interesting one. I haven't got a picture of it here, but it belongs to the same family that Puellina does, a cribiomorph bryozoan, and that was the most common one found on the Iranian Lepidocyclina. So there's a relationship there where that particular family of bryozoans seems to do well on growing on Lepidocyclina tests. Now these giant forams were sitting on the benthic forams that sat down on the seafloor they probably were deceased when the bryozoans started growing on them. So we've got dead shell material or dead tests sitting littered on the sea floor. Sometimes they may have been stacked one upon each other, and the bryozoans often prefer cryptic environments, so they may have actually grown on the forams after death, post-mortem, when they're lying in a heap, and the larvae of bryozoans could get in there and start growing on the surfaces. That was the thoughts of the people who did the study in Iran. Nowhere else in New Zealand do we really find such a high number of these big lipidocyclinas. They are just spectacular. For another 10 kilometers to the east of Taita Stream, out towards the Hokianga Heads, is a well-known lipidocyclina locality at Martins Bay. Again, it's Waitiiti Formation, but they don't reach over about 2 centimeters out towards the coast. Bruce looked at the remaining microfossils, the other foraminifera, generally less than 60% planktics. Quite interesting, though. Bruce's study of the Waitiiti Formation shows that the sediment was more than likely deposited at deeper than mid-shelf, even bathyal depths at places. So there's something going on here where we've got shallow water, large forams and bryozoans, but within the actual sediment, we have deeper water foraminifera. Those big rocks coming out of the Waitiiti Formation, spherical boulders, they are concretions, as I mentioned, but what they are is eroded material from the Mangakahia complex of the Locality. Punakateri sandstone is well known for its concretions, especially out towards the Hokianga Harbour, where we have Kotu boulders, a site similar to Moraki, where we have Cretaceous age concretion, so fossils in the boulders. And here in the Taita Stream, in amongst the Miocene sediment, we have Cretaceous concretions. However, the surfaces are eroded, pitted, bored into, and encrusted by other marine animals of Miocene age. So we call these hiatus concretions because they have been exposed at some other period, or in this case, the Miocene, before being redeposited and covered up by sediment again, only to come out in recent times. So Cretaceous age concretions with Miocene bioerosion and incrustation. A couple of the Cretaceous lithic fragments up the Taita Stream have Inoceramus, the Cretaceous bivalve. You can see some of the valves in cross-section on the lower left. There's a piece on the upper left where you can just make out some of the ridges on the surface of the shell. The shell itself gets quite thick and it has a prismatic shell structure. So this piece on the upper right, if you look down below, is a photograph of it from above. And you'll see in the center is a large boring, a circular boring through the shell, and a whole lot of bryozoans of different shapes and sizes growing on a piece of Cretaceous age shell. So these are actually Miocene bryozoans on a Cretaceous shell fragment. So I wrote a little note about that for Geoscience, and yeah, fabulous. There's over 12 species of bryozoan growing on that piece of Inoceramus. The original habitat, as I mentioned, all the signs were that it was a shallow marine. I guess we could call it a reef or a shoal where we have the stony corals, warm water, the rocky shoal was formed of local bedrock, so the allochthon, the concretionary Cretaceous sediments. But it's more complex than that because we have the deeper water forams in the mudstone surrounding the lithic fragments. And we also have some oceanic fossils within the Waitiiti Formation as well. Not all of the bryozoans I showed you were restricted to shallow environments. Some of them were mid-shelf species that may have been incorporated into the deposit. We have things like a nautilus shell, which seems unusual to find that in a shallow water deposit, so well preserved. So we have a mixture of both deeper and shallow water faunas. And this is not unusual in northern New Zealand. As Bruce has pointed out, there are similar strata in other basins, Waitemata Basin that you see here. Material being redeposited deeper in a sedimentary basin. So they're eroding, or some sort of event has caused a failure in the submarine slope. The shallow material was worked down into a deeper part of the basin. But overall, the Miocene has definitely got indicators of warm subtropical conditions. Thus, what a story. The Waitiiti Formation gives us evidence of a subtropical shallow rocky reef or shoal environment during the Otaian. That's before it was eroded and redeposited deeper in the basin. As I say, some of those rhodoliths and bryozoan colonies, they would have existed on the seafloor for months to years of growth before being moved and redeposited later further down in the deeper parts of the basin. So there was stability and then instability. Something happened. These strata, the Waitiiti Formation, were uplifted as the next big part of the Northland allochthon. The Tangahua volcanics were getting pushed up further to the north of the Taita Stream area. And then, as I say, Waitiiti Formation became part of the anticline above sea level, which began to erode, and eventually by 19 million years we had Waipua volcano starting to erupt, and we had basaltic lava flows from the west covering the area between about 19 and 17 million years ago. So long, complex story which goes on. This is a shot down at the Waimamaku River mouth, where we have conglomerates and some of the Miocene volcanics as part of the anticline. I'd just like to quickly take a quick tour through the bryozoan fauna, thanks to Dennis Gordon, who did the SEM work here, just to give you a little glimpse of some of the diversity. So of the bryozoa, as I mentioned, there were two main orders that we find today, the Cyclostomata. We actually found 9 representatives of 9 different families in the Waitiiti Formation up the Taita Stream. Tubular porines are probably the most common encrusters, with those little Lichenoporidae. Those are Disparella, the little circular radiating colonies of cyclostome bryozoa. And then the chylostomes, we have 10 anascan families, 18 ascophoran families, and we'll quickly go through some of these bryozoans now. These are cyclostomes, erect colony fragments, Actinopora, which you can still find living around New Zealand today, but this is an older species. These are quite delicate. The individual bryozoans lived in tubes in these particular colonies. and the little tentacle ring would come out of these orifices here. This one has a different aboral and underside, slightly different structure. Dennis was quite excited about this one, at least one new genus and species of Alicina. This one is the earliest known record of the genus. So this particular family of Bryozoa, they had quite large opesia, large oval gaps in the skeleton that was covered by a membrane, and the animal was inside here. They also had spines that covered this opening to protect it, and the spine bases you can just see in a ring around each apesia. Getting into the chylostomes now, the Aspidostoma, this particular species, Crateropora, was very common up the Taita Stream. Micropora, these ones are quite flat, but yeah, these are all SEMs where we're looking at individual zooids or individual animals within a colony. They may be, it'll be less than 1 millimeter from top to bottom of each of these. This one here, you can see the main primary orifice of this animal where the tentacles came out. But you might notice a bulge at this end, the proximal end of the zooid. This is actually a brood chamber. So you'll notice that this one does not have that bulge, but this one has that bulge that once housed the larvae. So this was a fertile colony, whereas this particular individual is a female brooding zooid, if you like. That's Staricamella. Macropora was one of the larger chylostomes we found. Here you can see the primary orifice covered by its little operculum there. That's a hinged, like cover, if you like, that would open up to let the tentacles come out of when feeding. And a huge ovicell, a huge brood chamber in Macropora. You can see on the right. They're almost, well, that one is bigger than the main body of the zooid. I love these ones. These are the Cribrulinidae on the left. This is one of the species that encrusted the Lepidocyclina. So we actually did have Puellina up the Taita Stream. This is one of the first fossil records of that from New Zealand. This one here of the family Inversulidae, the primary orifice of these zooids or individual animals is wider at the top and actually opens in reverse to most other bryozoans. So it's given the name Inversulidae because its operculum opened from the other side. We have had a really close look at this one, and I'm happy to report this is going to be published probably this week in a paper I've been working on with 2 other South American bryozoologists. We've named it Para-Inversula gordoni after Dennis, and it is the first New Zealand record of this genus. And there are Miocene records in South America. So we made a little bit of a story about that. That should be out this week. Pyrrhinidae, another erect bryozoan, the beautiful Siphonicteridae, another tree-like bryozoan, and a close-up of the individual zooids. Retiparella, very distinctive bryozoan. Here we see brood chamber or ovicell on the one in the center. This particular bryozoan is known from Indonesia. It's not I don't think there were any other New Zealand records of this. So this is a warm water species that turned up as a surprise in our Miocene bryozoan fauna. Relatives in Indonesia today. Escherichnidae, Crepidocanthidae. Again, a lot of these, the Crepidocantha is probably a new species. This one here, another new species. The Smetinidae. Here we have some little tiny bryozoans inside a larger zooid of a deceased, a larger bryozoan colony. Incredible SEM work by Dennis here. You really need the SEM to get the finer details of the taxonomy of bryozoa. The SEM is invaluable. So in summary, at least 75 species comprising 14 cyclostomes, 61 chylostomes. So it's enormous task to try and describe this fauna. A monograph is needed, probably need a few PhD students or something to work on this. But hey, it's I took advantage of the chance to share some of it tonight, so I'm pleased about that. At least we can highlight this deposit as being very significant for Miocene bryozoa. Future study. I just touched on the bryozoan morphology. I mentioned that they encrust hard substrates, and that's been one of the things that we've been looking at down in Wanganui Basin with the team from Europe, the Natural History Museum of Oslo and University of Oslo are interested in the evolution of bryozoa, especially things that occur within colonies and between colonies. We've got interactions occurring on some of the shells. This is one from Wanganui. Here's a SEM showing two different bryozoan colonies interacting. We could do this sort of study with some of the material from the Taita Stream. Paper has just come out on some of the material we looked at down in Wanganui, which looks at some of the life history traits within bryozoan colonies through time, how successful they might be, looking at the number of brood chambers, for example, what that's telling you about how fit, if you like, ecologically the colonies were, and how long before they reached maturity to produce young. There's all sorts of things that we can go into more detail. So yeah, changes through time, exploring patterns of macroevolution. So bryozoans form a great case study for that kind of work. Couple of references there. The key geology ones are Evans, 1994, and Bruce's work. I'd like to thank Diane, my partner, for accompanying me in the field. Dennis Gordon, of course, who did all the SEM work and also took part in the field. Bruce Hayward, we've had up with us in the field. Yeah, it's a team effort, and it's all done just in our spare time. So, you know, it's citizen science, if you like, but I've really enjoyed being a part of it, and hope you've found it interesting. A little window into a local story up in the Hokianga here that can tell us a lot, a window on the past, if you like, for Miocene New Zealand. Thank you.